Hello everyone. So this is going to be the second video in the AP Human Geography series. So this second topic is a introduction to maps. We will be looking at various types of maps and pretty much how to study these maps. So before we start looking at a map specifically, we need to understand what are maps. So pretty much, a map is a symbolic representation of selected characteristics of a place, usually drawn on a flat surface. So it pretty much represents symbolically various physical locations on a two-dimensional surface. In the simplest terms, that's pretty much what a map is. And cartography is the art and science of making maps and charts. So that's the profession which makes these kinds of maps. And we also need to understand, why is no map perfect? Because, no map can be fully accurate, and part of this is, all maps distort four factors, namely distance, area, shape, and direction. And the reason this distortion happens, the reason why all of these are distorted to some degree, is because mathematically you cannot project a 3D surface onto a 2D plane 100% accurately. So there are various methods in cartography which enable them to do this, but in that process they lose certain characteristics and they distort one of these four factors, or multiple of these factors to some degrees, and different maps distort different things. So there's a map for each purpose. So really, although there's distortion, it's not too big of a deal, because it really depends on what you're using the map for. So they'll just maximize specific areas and try to distort them to the least degree. So that's pretty much why no map is perfect. And if you really want a fully accurate representation of the Earth without any distortion, you need to get a globe, because a globe is a three-dimensional object, and because of that shape, it is not distorted and it's fully accurate. Um, the art of, specifically, the term for projecting three-dimensional surfaces onto a 2D plane, as discussed earlier, that's known as a projection. So you would project part of a globe onto a map, and obviously, even though globes are fully accurate, there are many situations where you can't use a globe. Um, Now, for example, simply because globes are difficult to carry around, they are three-dimensional objects. They are big spheres. You can't carry them around, unlike a map, which you can pretty much just fold and keep in your pocket. So that's pretty much the first part of maps. Let's look at a map more closely. Let's look at the parts of a map. So a map has four main parts. So first we have the title. Pretty much it tells us what the map is. Um, in the right hand example over here, on the bottom left corner, you can see that's the title, North America Political Map. That's what it is. What's a political map, you may ask? Well, we're going to get into it later. Um, but this is a map of North America, and it is a political map, which we will get to understand later, if that is you don't know already what a political map is. Now, second, we have a compass rose. The compass rose, try to see if we can locate it. It's actually right here where I'm pointing with my mouse. Pretty much, it defines the cardinal directions and sometimes the intermediate directions as well. So cardinal, pretty much north, east, south, west, and sometimes the intermediate directions, meaning northeast, southeast, southwest, northwest. So intermediate directions like that. And this is important because you need to know where is north, where is south, where is east and west. And this map is a really good example of why you need a compass rose, because normally if you look at it, you would just think, well, north, that's just straight up, south is straight down, east is literally to the right, but it's not exactly correct because as you can see, the compass rose is kind of curved because it follows the latitudes and longitudes, which we will also get to in a bit. But as you can see, it's always not that simple, so you need to define your directions, and that's why a compass rose is necessary. So that's the second part. The third part you have is arguably one of the most important parts, is the legend. Well, there are a lot of things on the map. In this map, there are a few things, but in some maps, they have a lot of things, and you need to understand what those things are, what those symbols are. What is this red line? What are these black dots and these white dots? Well, you can just look at the compass rose, and it defines these symbols. A white dot, that's a national capital, obviously. Capital of America, that's Washington D.C. And on black you have the major cities, so LA, San Francisco, Chicago, Detroit, you name them. And the red line, that's the country boundary, right? So pretty much the border, as you can see. Yep, makes sense. So pretty much that's what a legend is. Some maps, they have a lot of things, a lot of symbols, but this is one of the more simpler and I guess the common versions of the legend. Next, you have the scale. It's mathematically the ratio of the distance on the map to the corresponding distance on the ground. Pretty much, well, you can look at a map and you can look at it right now, but like really, on the map, Chicago and Detroit look close by, but like how much is that in real life? How many kilometers, how many miles? And pretty much that's what the scale is for. It shows you, just it's right there below the legend or in the legend, if you may, and it pretty much says, well, this much, if you can see my mouse, this much length of the map, of the actual map, corresponds to 600 miles in real life. So Chicago and Detroit, well, how much does that look like? It's like 200-ish miles, right? According to the scale. If you said that, you would be right, because in real life it is, a little over 200 miles. So, well, that's the final part of a map, the scale. There are many more parts, but these are the four most basic, which you really need to understand. Next, let's look at a map. There are a lot of things wrong with this map. It's not a good map. Um, well, maybe it's an incomplete map. Not necessarily, but um, that's what it could be. But well, I'm going to ask you, well, what's wrong with this map? Why is this a bad map? Now, um, if you think about it, well, it's pretty simple because it lacks a lot of these parts of a map. So a title, where's a title? Title tells me what this map represents. It doesn't have a title, so I have no idea what this is. A compass rose? Well, it doesn't have one either. Well, I could imagine one, and I would be almost correct, but it's still important to add a compass rose. Legend? Well, there's no legend. Legend would tell me, well, what are these colors? I have no idea. Scale? Well, how big is this map, like the actual map length compared to the real world map length? Real world length? Well, what is that? Um, well, you need to tell me that, but through a legend, but they don't, so that's another reason why this map is bad. So it pretty much lacks all of these things, which is why it's a bad map. On the right, you can see a challenge question. Well, you might not be able to answer it, but what is this map trying to represent? If you finish the course, you might be able to kind of guess what this map is trying to represent. Um, these colors, you might not know what they mean, but you can kind of look at patterns and compare them to real world locations to find out. So don't worry if you get it wrong, it doesn't really matter, but I guess it's a fun challenge question. So well, if you guessed biomes, you would be correct. If you didn't guess it, it really doesn't matter. But why I say that is because, well, look at this gray area. That's pretty much the Sahara Desert, right? And Saudi Arabia, that's also gray. And these places are deserts. So I guess gray corresponds to deserts or desert regions, desert biomes. Um, Green, perhaps that's rainforest. Why? Well, because this is the Amazon rainforest, Brazil. If you can see my mouse. So perhaps green corresponds to rainforests. and or you can see Australia, this light brown, maybe that's like dry lands or whatever. So um, with these hints, you can say you could, guess that, or it corresponds to biomes, but it doesn't really matter if you know it because it's not a good map. But if it was, you would have known straight away. Next, let's look at scale size. Um, it's a little bit different from map scale. The whole map itself also has a scale, so pretty much, um, as you can see there, it's similar to a map scale, as I said. So here, 1 inch on the map is roughly 1500 miles. Okay, um, and over here, 1 inch on the map is 20 miles. So um, this on the bottom, that's a much larger scale compared to the top. Maybe it's counterintuitive because you would think the one that zoomed out more has a bigger scale, but if it zoomed out more, it has a smaller scale compared to when it's zoomed in. And part of it is mathematically a representative fraction. The ratio between the map and the world, it's really small if it's really zoomed out. That's why they say it's small, and it's a much larger number if it's really zoomed in. So that's why they say a zoomed out map is small scale and a zoomed in map is large scale, because that's how it is mathematically. So even if it's counterintuitive, you can just try and memorize it. Let's also look at this. Which of these maps has the largest scale? I picked these two intentionally because they kind of look similar, but if you really look at it closely, well, the one on the right has a smaller scale and the one on the left has a larger scale. Because the left one is much zoomed in. It's the city of Denver, and it's a very specific part of Denver. You can see all the avenues, roads, there's the park. On the right, you can see Chicago, but it's kind of zoomed out. Um, you can't really see the roads, like, the roads aren't that large compared to the picture on the left. So the one on the right is a much smaller scale, or it's much more zoomed out. So that's pretty much scale, map scale. Let's look at latitudes versus longitudes. Well, the 3D sphere, there are horizontal and vertical lines on it, and these horizontal lines, those are called latitudes, and the vertical lines, those are called longitudes, and they're measured in degrees. As you can see, the closer it is to the pole, the higher degree it is. The closer it is to the equator, the smaller the degrees. I mean, well, the smaller the magnitude is, because really it's negative. So technically, the south, the lower you go, the smaller it is. So I guess you can think it like that. But in terms of um, magnitude, the smallest magnitude is the right in the middle. Okay, so that's the latitude. Longitude works literally in the same way, but it's vertical. And east is the positive angles, west is the negative angles, the way you express these longitudes, but they're pretty much the same. And instead of the equator, you have the prime meridian. It cuts through London, and that's right, it literally cuts the earth in half between east and west. That's the prime meridian, that's the equator. So let's move on. That's pretty simple. Let's do like an exercise, small exercise. How would you use these latitudes and longitudes? Well, pretty much they're used to identify very specific locations. So how you would do is you would just find the longitude, and then you would find the latitude. That's pretty much all it is. It's a coordinate. Think of it like a mathematical coordinate plane. This is the x-axis, and the vertical one, that's the y-axis. Okay, and you just find the x, comma, the y, or the longitude, comma, the latitude. That's how it works mathematically. Let's look at the red one. Longitude 0, that's London, right in the middle. The line passes through it, so that's a 0 longitude. And the latitude, well, I had to estimate maybe like 50-ish. So I could say the coordinate of the red point is 0, 50. If you look at the light green, it's in the middle of nowhere, but doesn't mean we can't identify the coordinates. It should be around negative 160-ish longitude, and the latitude is around, I guess, 20. So I could say that it's negative 160, comma 20. Let's do a final one. There, South Africa, Cape Town, around that perhaps. Longitude around 15, I guess, around 15, and the latitude is around negative 40 to negative 35, so around 15 comma negative 35. So that's how to use latitudes and longitudes to identify specific locations. Let's next look at the types of projections. So there are multiple types of projections. So here's the first one. So this projection is called a Mercator projection. Um, Pretty much, it represents the shape and direction accurately, but it distorts distance and area a lot. So remember the four factors? Yeah, so um, it distorts mostly the distance and area. The distortion on shape and direction are a minimum. And it's also rectangular. That's another positive thing about it. Easy to keep, I guess, and it's pretty popular actually. Google Maps, that's a Mercator projection. And many other websites and places use Mercator maps. One of the most famous maps, if I would argue. Next, this map is a Robinson projection. Um, the area and shape are well represented, least distorted. However, the direction and distance are the most distorted. Um, Often it's used in school classrooms because although direction and distance are distorted, it doesn't really matter because the more important thing is the shape and size of countries. Since that's the main thing, maps are useful in schools, so that's why it's popular in schools. And I also need to mention Mercator. I did say shape and direction are accurate. Um, it's pretty much all usually used a lot in navigation a lot since direction is really important in navigation. So that's one of the things that I forgot to say. This third map, this is very similar to Robinson, but is quite different. This is a Winkle triple, and all variables are equally distorted. Area, shape, direction, distance, all of them are distorted. Um, so perhaps that's a pro. Depends on your usage, and that could also be a bad thing. Maybe shape is really important to you. Maybe direction is really important to you. But it doesn't really matter since all of them are distorted equally. So if you're looking for, I guess, the most accurate per se graph, then it would be the Winkle triple. Next, this is a weird graph. I used this before and it's called the Good homolocine. So pretty much the shape and area are well represented, least distorted. However, the direction and distance are really distorted because of the interruptions, as you can see. It's shape. It's I guess the way it's projected is also quite strange because of these interruptions. But that's pretty much the good homolocine. Well, depends. Maybe it's quite useful to you. But that's pretty much what that is. And I mean, there are way more maps, but these four are the most, I would say, the most important and the most memorable ones. And actually, that's it for maps. And next lesson, we will be looking at various spatial concepts, pretty much space and various concepts surrounding it, etc. So I will look forward to it next week. And thank you for tuning in and listening. And with that, goodbye or farewell.